There's a whole lot of also very well-dressed people. I feel so underdressed. Who's specialty here? High concentration, very well.
They were all asking, do you have any Python experience? I was like, I will.
There we go. Okay. Well, let's get going. I hear that it is very important for Expo appearances to know Python, apparently, and have that on your CV. And soon enough you will. But until we get to actually applying Python, we do still have to review linear algebra, so let's wrap that up. So I have posted, so just in case you know somebody who has missed the lecture, do remind them that all of my lectures are posted on YouTube. They're not on Canvas, they're on YouTube. And as long as you know how to spell my name, you can find that YouTube channel, or you can go down Canvas and find where I posted the first one. So let's just briefly formalize, and I need to swap this place. All right. Formalize what we talked about last time. So I have introduced why is it important to do matrix vector multiplication. It underlines a whole lot of operations that you essentially take for granted on the computer or otherwise in science and engineering. And matrix vector multiplication was not put together there to torture young students. It's actually put together because it has a lot of important applications. So if you were into either movies or video games, every time there's a computerized version of something, let's say that the actor is supposed to do a very complicated flip, and they don't want to break the back of a famous person, they can actually do that by aid of a computer visualization and actually rotate the image of a person. Right? Maybe just having a couple of different poses of that actor to basically improve the appearance. But that's actually just translation, rotation, any kind of stretching. That's really just multiplying a matrix with a vector of position. Now, of course, every person or any object on the screen is just, it's a bunch of pixels, okay? And voxels really in 3 dimensions. But it's still a bunch of positions. And for each of those positions, you just do a matrix vector. Each position is described with a vector. Matrix vector multiplication, and you will get this new position. And now computers, of course, can do thousands of those operations really quickly, and they can play that in front of your eyes really quickly, and you will not even see the difference between the real thing and what's actually a computerized version. So that's one instance. Another instance, and you will learn soon enough, concept of stress, both in transport phenomena and in mechanics, solid mechanics and geomechanics. Okay? And the way I get stress is a tensor here, right? But that's because it acts from all sides. And to describe how it acts on anything, I need a fundamental description of it, of how it acts in 3 different directions. Okay? And in itself, it's something that is a vector field. So 3 times 3, I get 9 descriptors, and they form a matrix. And ultimately, once I have that fundamental matrix in a coordinate system, to get stress action on any other plane, I just need a normal of that plane, so the direction normal to that plane, and I multiply tensor with that direction, and I will get stress in that direction. Okay? So that's why, for instance, matrix vector multiplication is very important in mechanics, be it solid or fluid mechanics. And that has a lot of important implications, and you will get to those in the respective courses. So I need to do also all kinds of transformations for these matrices because before I can do anything to them, so I can always add 2 matrices as long as they have the same dimensions. So that means the same number of rows and the same number of columns. I can multiply scalar times a matrix by multiplying every element of that matrix. Okay. I can transpose a matrix that's just simply flip whatever was a row becomes a column and the other way around. Okay. And you will get in your homework a lot of exercises to do this mechanics. Now vectors we can see as matrices. And if we see them as matrices, then it's kind of very important who is a row vector, who is a column vector. And row and column vectors are not regarded as the same object. But fundamentally, vectors are actually one dimension. So if I'm not embedding them into the matrix row, okay, then they're just rows of numbers. And as long as they have the same number of elements, it's all the same. So I'm going to just briefly comment on that because it's relevant to your homework. So just note that when I write something like, let's say that U is a vector and U is 1, 2, 3. Every time I don't want to think of a complicated vector, I name it 1, 2, 3. The numbers, they're easy to make up. So if I'm asking, hey, what is a U transpose? Okay. The moment I'm asking what is a U transpose, it is important that this is indeed a column vector, right? And U transpose becomes a row vector. Yes? So this is a column vector. And U transpose is then a row vector. 1, 2, 3. So again, the moment I'm talking about U and U transpose, who is a column, who is a row, matters. Okay? And this, so row, column business is important, and I am, in my mind, embedding vectors into the world of matrices. Why? Because I want to multiply them together. And I already mentioned why is it important to multiply them together. So, for instance, in this particular case, if I'm asking you, and I'm just going to work with U, if I'm asking you what is U tau, U transpose U. The moment I'm presenting it this way, I'm thinking about matrix multiplications, matrix vector and matrix multiplications, and who is a row vector, who is a column vector matters. So when I have U transpose U in this case, U transpose is 1, 2, 3, and U is 1, 2, 3, correct? So the first one, what is the dimension of the first one, if I'm thinking about it as a matrix? 1 by 3. Dimension of the second one is, what did we say then the result has to be? 1 by 1, or just a scalar, right? So this is 1 by 3, and this is 3 by 1. Therefore, the result is 1 by 1. So this result, as we already said, is that the way I multiply this is I go 1 times 1 plus 2 times 2 plus 3 times 3 in this case. And that is 1 plus 4 plus 9. 14. Now, what is U transpose? Can I do that? It is 1, 2, 3. 1, 2, 3. What should the result be? 3 by 3. Okay? And we have immediately gotten the evidence of something, is that in the world of matrices, when I'm multiplying them, I can't just flip the order. U transpose U and U transpose are two different things and could even have very different dimension, let alone anything else. Okay. So here, this now becomes, okay, I know this rule. I take the first row of the matrix, the first matrix when I'm multiplying them. In this case, it's a simple vector. And it's a simple number. First row is just this 1, right? Times the first column of the second matrix, which is also a vector, and that's also just 1. So in my first position here will be 1 times 1. Okay. Then I take the first row times the second column. So again, a simple one, 1 times 2, and then 1 times 3. Does everybody see this? It's a very simple row. Okay. It has one number. And then a dot product with a very simple column, which is also one number, just gives me that. And then I keep going, so it's 2, 4, 6, and 3, 6, 9. So ultimately, this is 1, 2, and 3. Okay? So this is a 3 by 3. So this is a 3 by 1. This is 1 by 3. And the result is 3 by 3. So in matrix multiplication, order is important. So U transpose U is not the same, not even the same dimension, let alone anything else. Now, sometimes it's going to be the same dimension. But most often it's not going to be. Questions? Yes.
With the 14, is it still in brackets or is it just by itself?
That's a formality. Yes, I could put brackets and then I'm thinking about it as a matrix. Okay? Now, thanks for pointing that out. If I was representing things on a computer, so mentally, we immediately map that onto one number. And whether that one number is considered a table of numbers or just one number, mentally the same thing, right? However, if I was storing things in a computer, I have to give computer very clear instruction what type of memory to allocate, how much, and what is that type of spot where I'm putting things, okay? If you think about it, it's like putting things into a pantry or a fridge are not the same things, right? So you gotta tell it, is this a pantry or is this a fridge, wherever it is that you're putting your can of something, okay? Now, they could work the same, you know, a can of beans is just fine, whether it's in a pantry or a fridge, or a bottle of milk is not. Okay? So it's sometimes important, sometimes it's not, but computers do want clear instructions. So you have to clearly define an object where you want to store numbers. And whether you're defining it just as a number or a matrix can matter quite. Okay? So thanks for that question. So yes, this is formally a 1 by 1 matrix. So it's a one number, so I can think about it as a scalar. Does this make sense? Okay. So in your homework, there will be a whole lot of questions. Hey, can you do U transpose W and W transpose A and so forth? And it's really just like it's going to be a mind game of these dimensions, whether they match and whether you can do something. Now, one more thing that I want to point out is that in terms of the definition of a scalar product with two vectors, so now I'm going to add myself a vector. I'm going to save this first. So I had this U as 1, 2, 3, and I'm going to B as 1, 0, 1. Oh, hi. Now your slides say that the definition, this is two vectors in space. If I have two vectors in space, they define a plane. And in that plane, I can look at this. If I put literally a piece of paper going through these two vectors, I can look at the angle between them. That's the definition of an angle between two vectors. How do we get that angle? We get that angle, your slides say, by saying cosine theta, and I think we went over that briefly for 2D, as U transpose V Now, this is a definition that formally works only for column vectors, because U transpose will be a row, and then I'm going to multiply it by a column and get one number. Okay? Yes? So this formally works, this definition, formally works only for column vectors. There's another definition of a scalar product that just looks at these, because it's a scalar product of vectors, and it doesn't really matter whether those vectors are matrices or not, or considered as rows or columns, that just goes and says, hey, this is sum of I is equal to 1 to n ui vi, when n is number of these elements, and the norm of u2 norm. Okay. And this is quite frankly the definition that matters here. So I could have these vectors as column vectors or row vectors. It's okay either way. They're triplets of numbers that describe coordinates in space. So it's really the second one that is this definition works for row vectors and column vectors. Vectors, and is more widely applicable. So in your homework, I actually want you to exercise this a little bit. Okay? How do you think about these objects? Because it's actually often important later in applications. How do you describe your objects to a computer and then use that consistently? Yes?
It doesn't matter if it's U transpose V or V switch.
So here, if I actually if I did, for instance, in the first definition, UV transpose, it matters, because UV transpose would be what? Different. It would be a table of numbers, right? And then I can't look at that as a cosine of an angle anymore.
But I mean V transpose U.
V transpose U, in this case, it doesn't matter. Okay? Because U transpose V and V transpose U, if it actually exists as a single number, it's the same thing. Okay? However, if it's not a single number, but it's a matrix, then it's not the same thing, it's transpose. Formally, if I have transpose of everything, or of anything, let's say that I have two matrices, A, B transpose is B transpose A transpose. And that's because I have to flip dimensions, right? So I have to reorder which matrix I'm multiplying first. So formally, U transpose V in this case, transpose is V transpose U transpose transpose. And when I do transpose twice, what do I go back to? The original. So indeed, U transpose V transpose is V transpose U. So it doesn't matter in that definition, because again, it's that one number. However you flip it, it's going to be fine. Okay? Now again, these exercises will look a little mechanical, like why are we doing all of this? But it's important exercise in manipulating these objects. And you can manipulate them through linear algebra, and that allows a whole lot of very important theory, solid mechanics, for instance, right? But it also enables storing these things in memory and flipping things virtually, even if I'm thinking about flipping an actor in a movie, okay? Which can make a whole lot of money. Now, in your applications, you will get to the reservoir engineering, and you will get to the reservoir simulation. And the way I describe my field is with a vector or vector numbers if I'm describing it only through the Wellbore. But an actual field is a matrix, three-dimensional matrix, typically of permeabilities and porosities that I work with. Okay? So it's important that you, in your mind, are able to manipulate those objects or in a computer. You can't do a million objects in your mind even if you really wanted to, okay? So that's computers are an important extension of what we do. Okay, excellent. So let me just now go back to the PowerPoint. I hope this answers some of the questions that you didn't even know you had about the homework. Did you look at it? Due on Friday. Okay, just checking. So we went through the multiplication of matrices, and I did examples that were smaller matrices. I can formalize that often I have a table of numbers, and that table has m rows and n columns, okay? And I'm multiplying that with a vector that has n rows. So then I have m by n times n by 1. The result is m by 1. Okay? So formally we write that AX is equal to B. Okay? So that is how we often, this really can be looked at as a linear combination of these numbers if you think about it. So when I look at what is B1, B2 through Bn, okay? I can write down what do I do when I do multiplication. I multiply that row with a column and I get this. Everybody sees it? So when I multiply that row times the column, it's A11x1 plus A12x2 plus all the way to A1nxn. Everybody with me? This row times this column is A11 times x1 plus A12 times x2 and all the way to A1n times x1. That's this. Yes? This is just generalization for any case. And then I do that with the second row times the column. That's this. And third, and ultimately the last row, which is mth row times the column, which is this. Okay? So when I actually look at it, hey, there's this x1 that appears all the way here, and x2 and xn. So it looks like this column vector is x1 times first column of A. This is the first column of A, yes? Plus x2 times second column of A, and all the way down. So technically, this result, this B here, is x1 times first column of A, plus x2 times second column of A, plus xn times nth column of A. So it's a linear combination of columns in A. You can look at it that way. So this is basically what that is. That's just another way to look at this A times X product. Okay. So, and again, whether I multiply vector with a matrix and matrix with a vector does matter. Sometimes I cannot do it, okay? And I have to look at the dimensions and whether vector is a column vector or a row vector and what are its dimensions matters in this type of multiplication. Okay. And then if I do the two matrices, it's really the same. I just repeat matrix vector multiplication and I just keep going down the columns of this second matrix. Yes?
If you were to just multiply a matrix by a scalar, you just multiply a scalar by each part of the matrix?
Yes. So So if I have a scalar, it's relatively easy. Just every element that I have in the matrix, I just multiply with that scalar. Okay? And the same with vector, scalar times a vector. Okay? So if I had another matrix, I would kind of just go down this column. Okay? Okay? So basically, formally, if I had this matrix times the second row, in general, if I looked at any, so this is a matrix times a matrix, the result is a matrix. So in this particular case, I have a 3 by 3 and another 3 by 3. When I multiply them, the result will be 3 by 3. So that much is simple. But any element in that resulting matrix, if that element is in position, say, 2, 2, okay? When I have C2, 2, first number 2 refers to the row, and second number 2 refers to the column, right? C2, 3 is the second row, third column, right? Right here. C2, 3 is second row, third column. C2, 2 is second row, second column. It's off again, or it's not fast? Okay, so C2, 2 is second row, second column. I gotta watch there what I'm doing, apparently. And second row, third column, right? So how do I actually get this C2, 3? I take the second row of matrix A and the third column of B. And I do the scalar product. Okay. And I can have as many rows or as many columns, but that's essentially the result. So any sort of, this is again formalizing it, any sort of Cij in this resulting matrix hanging out somewhere in the middle of the matrix at the crossroads of the ith row and the jth column, the way I get it is to take ith row of A and jth column of B and do a scalar product. And I can do that scalar product because if I'm actually doing this to begin with, they should have the same number of elements. Yes? Now, why am I formalizing this in a most general way like this? And I'm going up to some m number of rows, n number of columns. There's this middle dimension that is R. Why am I bothering? Why don't I just explain things on a 3 by 3 matrix and move on?
Find the general form.
Yes, I want the computer to do I don't need a computer to do a 3 by 3 matrix for me. Okay, that we can do. 4 by 4, with a little bit of effort, you're going to start making mistakes. 5 by 5, every student will, no. And 5 by 5, I have quite a bit of training. I'm not doing 5 by 5, I can't. I go to computers for that. Okay? Because I know how to program them. Okay? Now, that's the whole point. I want computer to do 1,000 by 1,000. Then I'm not, nobody's doing that by hand. Now, I want the computer to be able to, just to throw a matrix at it, and computer will say, aha, the size of this matrix is whatever it is, million by 2 million, okay? Therefore, I'm going to now multiply it with another matrix that is 2 million by 3 million to get a million by 3 million. But then he will come along and says, 3 million not enough, I want 5 million or 5 billion or whatever it is, right? So I want computer to act accordingly depending on whatever number I throw at it, right? Whatever size I throw at it. So I need to generalize. And this is the biggest sort of mind step from like doing a little simple linear algebra to going to put it to computers is in order for it to be useful, it has to be general. In other words, if I write a program, and I write a program that only multiplies, and now it's not, okay, it's kind of just lagging a little. I write a program that multiplies a 3 by 3 matrix with a 3 by 3 matrix. And I can go down the line and say, C11 equals A11 times B11 plus A12 times B22. Get the catch my drift? So I can do that. And then I have something that works only for that specific case of 2 3x3 matrices. That's not useful. I wanted to go to 1000 by 1000. But in 1000 by 1000, I'm not going to write A11 times B11 plus A12 times B21 plus A13 times B31 plus A14 times B41 and keep going to 1000. I'm not going to type that in. Okay? So I need something effective that will be generalized and say n is 1000, go. Okay? Keep adding. Okay? We will formalize that. There's something called a loop in programming. It's very good at repeating, but I need to give it a pattern. And that pattern has to look cryptic. Just like that. So that pattern, so we will actually learn to formalize what used to be my I can do what? This already. So I can do any kind of, I don't want to write the following. I don't want to write, in this particular case, U11 V1 plus U2 V2 plus U3 V3 and be stuck with that. Okay? I want that more generally. This is a sum, and this is my letter sigma, from I from equal to 1 to 3, Ui, Vi. Okay? And more generally, I'm just going to say, hey, n right now is 3, but this is a sum from I is equal to 1 to n Ui, Vi. Okay? And then I just go and change n to 1000, and this still works. It can be 1000, it can be million, it can be billion, whatever it is. And we will find a way to type that as a program, but essentially all I'm changing is that n at the beginning. That's it. And that will become a function that depends on this number n, and every time I give it a different n, it's going to work differently. Yes? So this is, as a mind, in your mind, you're actually doing quite some major steps. So even if it takes you a moment, because those are major steps, okay? Being able to basically scale things up and just then let the computer, and that's what computers are not particularly smart. They're as smart as they're programmed to be smart. We have to tell them everything to do, but they appear smart because they can do 1000 operations quickly. Okay? And if you tell it based on the 1000 different outcomes what to do, they will appear like they're doing some very smart decision making. But you programmed it. Okay? An engineer programmed it. Okay? So they appear very quick and smart in their decisions, but ultimately those decisions are programmed. Okay? Okay. Let me just see whether I have gone through all of the slides. So again, this is my general view. So this would be, can you write this as a sum? Take a piece of paper. I have m by r matrix, and I'm just showing you ith row. And I have an r by n matrix, and I'm just going to show you the jth column of it. And I want you to write the Cij as a sum with that sigma. So Cij is and that sum should not use I because I is already used. So come up with a different letter. be anything, but not I or J. How do you call that letter that you're using? Doesn't really matter. So that's Cij, and I use comma. I sometimes use it, I sometimes don't for speed, but it's ith row, jth column element. So Cij is what? I should use a different piece of paper. So Cij is what? Anybody? You can make a mistake, don't worry about that. So I have A's and B's. And all of the A's are from the ith row, right? So they're I, comma something. And then I have B's that are all in the jth column. So they're something, comma j. Yes? I1, A, I2, I1. So this sum, formally, it goes up to R. This sum is AI1, B1J plus A1, I2, B2J plus, and I keep going, right? And the last one is which one? R, B, R, J. Right? So now I want to write this as a sum. And what's changing here is this. It's kind of 1, 1, 2, 2, all the way to R, R. Yes? And that's the pattern I'm trying to formalize and recognize. So I need to give it a name. I called it a something. Something is perfectly fine as a name. Computer couldn't care less. It's for you, it's a drag to write all of that down. So I'm going to call it S instead. Okay? S goes from what to what? 1 to R. So these are the steps. Like you kind of have to recognize, you have to look at it a little. Don't be afraid of it. If it's easy or easier, don't use R, go up to 3. Okay? And then replace that 3 with R, if that's easier to look at. Okay? So just recognizing a pattern. Now I can go and tell computer, this is AIS. Okay? Now, all we need in the next step, we need a programming language. We need to figure out how does that programming language refer to vectors and matrices, and how does it store them. So what language does it use, okay, to refer to them? And how do I refer to ij element or something? Okay. And then I'm good to go. Then I just tell the computer to, in this, what we're going to formalize as a for loop, how to go and add these numbers one by one, as many as I need, as many as I have in the memory. But did you see mentally? And now all of the programming languages, the way they really differ is how they store these matrices and how they go through it and how quick they are at adding. Okay? And this is now where it's actually important, these languages, they're in between you and the computer memory. Okay, and they're telling where to go in computer memory. So that part is computer engineering and how fast that happens. I don't know much about that really. I'm always in this programming end. But what I do know is that it matters how things are configured in a computer, and that's what makes these chips and how they're designed relevant, because they keep getting faster and faster and faster, right? So there's somebody who designs that to be really fast. It's literally like, how fast can I go to the upper row to grab something and come back, right? Speaking of pantries and fridges and whatever, if my fridge is too clumsy and I need a chair to get to the top row, then I'm going to be slow, okay? So in that sense, the designing how fast something happens in memory, that's not what we're typically concerned about. There's electrical engineers that do that, okay, computer engineers. But we are going to be concerned about telling computer what to do and how to grab something from memory. And for that, we need a language. We're going to use Python. And maybe you have already learned on Expo that Python is to-go language right now, so that's what we're using for that reason. Okay. My computer is not happy today. The mouse just keeps locking up. All right, so again, we can also easily from this rule see if I just grab any two numbers and I kind of do this differently. So if I flip B's and A's, I can see that I'm referring to different memory locations in A's and B's. So even from that, I can immediately see that even in this context, AB and BA are defined. They're both 3 by 3 matrices, but they're not necessarily the same matrices. And if I just write down what is C22 in both of those cases, AB versus BA, I will see that I have a different sum here. Okay? And that sometimes could be the same, but most often it's not. So order matters, and AB is not equal to BA. Okay? Just to define an identity matrix, because it's an important matrix, so therefore it has a name. It sort of functions as a number 1. So I know that I have 1 times 3, nothing happens, 3 remains 3. 1 times 300, nothing happens, 300 remains 300. And I can do 1 times 3 or 3 by 1, 3 times 1, same thing. Identity matrix is that matrix. If I multiply another matrix with identity matrix, nothing happens. So if I have an identity matrix times another matrix, I will get the same result. So we typically refer to it as I, so I times A is the same as A times I, assuming that both of these things are defined. So if I have square matrices, they are. Square matrix has the same number of rows and columns. An inverse is then defined, A inverse, as a matrix such that when I multiply A with that inverse matrix, I get identity matrix. So it's again a parallel of when I think about numbers. When I have matrices and identity matrix. So when I have number 2, 2 times 1, and 1 times 2 is 2. Okay. At the same time, I know that for 2, any non-zero number, I have an inverse of it, which is 1 over 2, that gives me 1, right? So equivalent of that is inverse of a matrix, okay? So I could have matrix A, I, and I, A is equal to A, assuming square matrices. And I could also possibly find an inverse matrix A such that multiplication A times A inverse gives me identity. It's the same thing as A inverse A. So this is matrix inverse. And this I is identity matrix. So they're really just generalization of a number 1 and inverse of a number. It's just that now I'm working with matrices. Why is this all important? It's very important in so-called linear systems, and I'm just going to briefly introduce the simple linear system. x1 minus x2 is equal to 1. x1 plus x2 is equal to 3. Everybody has seen this? Just give me 1 minute, please. So I can actually write this down as 1 minus 1 times x1, x2 is equal to this first. 1 times x1 times minus 1 times x2, that's this, is equal to 1. And the second row is then what? So this is now my matrix of coefficients A, this is unknown x, and this is B. A, x is B, is linear system. By the same token, I can drive this to 1,000 of them, right? So it's important to have that representation.